The rise and fall of the levitating bus, unpacking China's vision for future transport. China has long been a front-runner in adopting and developing advanced transportation technologies, from high-speed rail to intricate urban metro systems. Among its more ambitious and ultimately controversial innovations was the concept of a levitating bus, often conflated with Maglev technology. This article delves into the details of this ambitious project, its operational principles, historical context, and the broader implications for urban mobility. One, the concept, an elevated vision for urban mobility. The project, widely referred to as China's levitating bus, was officially known as the Transit Elevated Bus, TEB, or sometimes the straddling bus. While the term Maglev was often associated with its futuristic appearance, it's crucial to clarify that the TEB was not a true magnetic levitation system. Instead, it was an elevated, electric-powered vehicle designed to run on fixed rails installed on either side of the road, allowing regular cars to drive underneath it. Operational principles and technical aspirations. The core idea behind the TEB was simple yet radical. Utilize the space above existing traffic lanes to transport passengers, thereby alleviating congestion without requiring underground tunnels or extensive new elevated highways. Elevated structure. The bus was designed to be approximately 4.5 meters, 14.8 feet high, creating a tunnel-like space underneath for vehicles up to 2.1 meters, 6.9 feet tall. Wheeled system. Unlike true Maglev, which uses electromagnetic forces for both lift and propulsion, the TEB was propelled by electric motors and ran on rubber tires along the side rails. The levitating aspect referred to its elevated position above traffic, not magnetic levitation. Modular design. The TEB was envisioned as a modular system, allowing multiple carriages to be linked together to increase passenger capacity. Each segment could carry up to 300 passengers. Power source. It was intended to be entirely electric, powered either by overhead catenary lines or potentially rechargeable batteries, aiming for zero emissions. Speed. Projected operational speeds were relatively modest for urban environments, around 40-50 km/h, 25-31 mph. For comparison, a true Maglev system, like China's Shanghai Maglev train, operates on principles of electromagnetic suspension, EMS, or electrodynamic suspension, EDS. EMS systems use electromagnets attached to the train that wrap around a guideway, lifting the train by magnetic attraction. EDS systems use superconducting magnets on the train to induce currents in the guideway, creating repulsive forces that lift the train. Both eliminate friction, allowing for much higher speeds, up to 600 km/h for the latest Chinese prototypes, and a smoother, quieter ride, but require dedicated, highly precise guideways. The TEB lacked these fundamental Maglev characteristics. The concept of a straddling bus dates back to at least 1969, with designs patented in the United States. However, it was in China that the idea gained significant traction in the early 21st century. 2010, the transit elevated bus concept was first publicly showcased at the 2010 Beijing International High-Tech Expo, drawing significant international attention. Its designer, Song Yuzhou, proposed it as a revolutionary solution for traffic congestion. 2016, after years of proposals and prototypes, a full-scale test model of the TEB1 was unveiled and underwent its first road test in Qinhuangdao, Hebei province in August 2016. The event garnered massive media coverage worldwide, with many hailing it as a potential game changer. Post-2016, enthusiasm quickly waned as practical challenges and controversies mounted. Doubts arose regarding its safety, technical feasibility, and the potential for financial fraud by its developers. 2017-2018. The Qinhuangdao test track was abandoned, and the prototype bus was left neglected, becoming a subject of public scrutiny and ridicule. The project's primary investor was accused of illegal fundraising. 2019, the test track was finally dismantled and the TB1 prototype removed, officially marking the end of the project. It's important to differentiate the TB's fate from China's successful Maglev train projects. The Shanghai Maglev train, opened in 2003, was the world's first commercial high-speed Maglev line, connecting Pudong International Airport to the city center at speeds of up to 431 km/h. More recently, the Changsha Maglev Express, a medium-low-speed urban line, opened in 2016, demonstrating China's capabilities in applying true Maglev technology in different contexts, beyond comparison with traditional transportation systems. The TB aimed to offer advantages over traditional buses and even subways, but also faced significant limitations. Infrastructure cost: TB lower than subway, no tunnels; traditional bus, low, use existing roads; subway, metro, very high, tunnels, stations; true Maglev, high, dedicated gateways. Traffic congestion: TB potentially alleviates, straddles traffic; traditional bus contributes to, subway, metro. None, underground; true Maglev, none, dedicated guideways. Passenger capacity: TEB, high, up to 300 per segment; traditional bus, medium; subway, metro, very high; true Maglev, high. Environmental impact: TIB, zero emissions, electric; traditional bus varies, diesel, electric; subway, metro, zero emissions, electric; true Maglev, zero emissions, electric. Integration with urban fabric: TEB, difficult, fixed rails, height; traditional bus, easy flexible routes; subway, metro, Minchu, seamless underground; true Maglev, difficult, dedicated guideways. Speed: TEB, moderate, 40-50 km/h; traditional bus, low to moderate, traffic dependent; subway, metro, high; true Maglev, moderate to high, urban specific. Safety concerns: TB, high, interaction with vehicles; traditional bus, medium; subway, metro, low; true Maglev, low. Flexibility: TB, low, fixed routes; traditional bus, high, route changes; subway, metro, low, fixed routes; true Maglev, low, fixed routes. The TB's primary theoretical advantage was its ability to bypass traffic while utilizing existing road space. However, its practical design introduced significant new challenges that outweighed these benefits. True Maglev systems, while costly, offer unparalleled speed and efficiency over dedicated long-distance routes and silent operation for urban applications. Had the TB been successful, its impact on urban transportation could have been significant. Urban transportation infrastructure reduced congestion by allowing cars to pass underneath. It aimed to free up road space, particularly in peak hours. Simplified infrastructure compared to building new subway lines, which involve complex and costly tunneling. The TB's elevated track was presented as a quicker and cheaper alternative. However, the requirement for dedicated lanes on existing roads, the need to modify overpasses, and the structural integrity required for its weight presented their own infrastructure hurdles. Visual impact: the large elevated structure would have significantly altered urban aesthetics and potentially blocked sunlight to buildings. Environmental considerations. Reduced emissions. As an electric vehicle, the TEB promised to reduce tailpipe emissions and improve air quality in cities. Noise pollution. Electric operation would have meant significantly less noise pollution compared to diesel buses. Energy efficiency. The efficiency per passenger kilometer was a key consideration, though the energy required to move its massive structure needed careful assessment. Examination of current implementation status, challenges faced, and future development plans. The TEB project, particularly the widely publicized prototype, is currently defunct. It faced a confluence of technical, safety, financial, and public perception challenges. Technical challenges. The rigid, long body made sharp turns on urban roads extremely difficult. Limiting route flexibility. Interaction with traffic. Concerns about how taller trucks would safely navigate underneath, and the potential for collisions during lane changes or emergencies. Structural integrity. The vehicle's weight raised questions about the durability of the elevated tracks and overall system stability. Safety concerns. Emergency exits were not adequately addressed, and limited vehicle clearance posed risks for larger commercial vehicles. Financial and regulatory issues. The project was plagued by accusations of illegal fundraising and investor fraud, leading to a loss of public trust and withdrawal of support. Lack of clear regulatory frameworks for such a novel vehicle type further complicated development and deployment. Future development plans. For the TEB concept specifically, there are no active development plans in China. The project is largely viewed as a cautionary tale in ambitious urban planning. However, China continues to invest heavily in true Maglev technology, focusing on high-speed intercity connections and potential urban applications. The development of a 600 km/h Maglev prototype underscores China's commitment to pushing the boundaries of magnetic levitation for rail, distinct from the TEB's approach. 6. Scalability and potential applications beyond China's borders. The TEB, in its original form, demonstrated severe limitations in scalability and practical application. The fundamental design flaws, safety hazards, and infrastructure requirements made it unsuitable for widespread urban deployment. Its fixed rail system offered little flexibility, and the integration into complex urban traffic environments proved nearly impossible. Therefore, its potential applications beyond China's borders were never realized, nor is it likely to be adopted. In contrast, true Maglev technology holds significant potential for scalability and international application, particularly for high-speed intercity travel, connecting major metropolitan areas with rapid, efficient, and environmentally friendlier transport. Countries like Japan, SE Maglev, and Germany, Transrapid, have also invested in this area. Medium-speed urban-suburban corridors. As seen with the Changsha Maglev, it can offer a quiet and smooth transit option for specific routes where conventional rail or metro might be too costly or disruptive to implement underground. The primary barriers to broader adoption of true Maglev globally remain the extremely high initial capital costs for infrastructure development and the need for dedicated exclusive guideways, which can be challenging to integrate into existing urban landscapes. The Chinese Levitating bus TEB project represents a fascinating, albeit ultimately failed, attempt to innovatively address urban congestion. While its futuristic vision captured global imagination, its practical implementation was hampered by a multitude of technical, safety, and financial challenges. It stands as a powerful reminder that groundbreaking ideas must withstand rigorous scrutiny of engineering feasibility and real-world applicability. Despite the TEB's demise, China's broader commitment to advanced transportation, particularly in true magnetic levitation technologies for trains, continues unabated. The lessons learned from projects like the TEB will undoubtedly inform future endeavors, pushing the boundaries of what is possible in urban and intercity transport. The pursuit of faster, greener, and more efficient ways to move people remains a global imperative, and the journey is often as informative as the destination.